Hello friends, welcome to the channel Physics by IITians. In this video, we will discuss BJT related questions that were asked in the UPSC mains physics exam. We have already discussed many questions related to BJT, but most of the questions were connected with the NPN transistor. We know that the BJT can have two different polarities. One can be a NPN and another can be a PNP transistors. In this video, we will discuss a question related to the PNP transistor. Okay, let's start with the question. So this is the question that were asked in the UPSC mains. Here, the beta for the transistor is given as 100. Let me start the recording, just a moment. Yeah. So the beta for the transistor is given as 100. This is given here. Then also it is given that this is a PNP transistor that can be understood from this arrow. This arrow is going like this here. So that indicates that this is the emitter junction and this is the base junction. And here we have a collector junction. So now that this arrow actually indicates the direction of the emitter current. So you can see that the emitter current is upward. You can write it as IE. And in this case, the emitter resistance is given as 500 ohms. And also the base resistance is 7 kilo ohms. And there is a base biasing voltage 3 volts. Here we have a V0 output potential and the resistance at the collector junction is 3 kilo ohms, and also it is having a biasing of negative 10 volts. And here we have a grounding at emitter. Now the first part of this question is find if the silicon transistor is in cutoff, saturation or in active region. That means we have to identify the region of operation of this particular transistor. Second part of this question is to find this output voltage V0. Then the third part of the question is find the minimum value for the emitter resistance. In this case it is given as 500 ohms, but it is asking that what should be this value. Let's suppose this is R. So what should be the minimum value of this R resistance so that the transistor will operate in active region. Okay, these are the three different parts of the question. We will go sequentially. Okay, let's first understand the meaning of cutoff, saturation and active region of a transistor. So as we can see from the diagram, the transistor actually has two junctions. So if this is the emitter junction, this is the collector junction and this is the base. So first junction is base emitter junction. So this is base emitter junction. Another is base collector junction. So if I write it in a more useful fashion, so actually the transistor has three semiconductors. One semiconductor is this, another semiconductor is this. The 1 and 2 semiconductors are of the same polarity. Either they will be the p type or they will be the n type. So if we sandwich a p type semiconductor between two n type semiconductors, we call it as a NPN transistor. Similarly, if we sandwich a n-type semiconductor between two p-type semiconductors, we call it as a PNP transistor. In any of the case, the sandwiched semiconductor, that is the middle semiconductor, actually forms the base. So this is our base. The left and right actually forms the emitter and collector junctions respectively. So this is the emitter base junction and this is the collector base junction. And we have to see whether these junctions are forward biased or reverse biased. Now, what is the meaning of forward bias and reverse bias? Let's discuss that also. So, the basic semiconductor device is a diode, and if we have a diode, so for a diode we have two junctions. So in the diode we have only n-type semiconductor and another is the p-type semiconductor. And this is the junction, N and P junction. This can also be written by symbol this. This is the simplified symbol for diode. So I am talking about a diode here. We are actually trying to understand what is the meaning of forward bias and reverse bias. So for this diode case, this particular junction is called the N and this is our P. So if the potential across the N junction is more than the potential across the P semiconductor, then we will call that the diode is in reversed biased. Similarly, if the potential across the n-type semiconductor is less than the potential across the p-type semiconductor, we will call it as a forward bias. In short, we can write it as RB, reverse biased, and this as FB as forward bias. So this is the case for the diode because there is only a one junction, but for the transistor there are two junctions. So we will call, means these two junctions can independently be forward biased and reverse biased. Similarly, this junction can also be forward biased and reverse biased. So based on the permutation and combination of this forward bias and reverse bias of these two junctions, which junctions? Emitter based junction and collector based junction. So we will have the active region, the cutoff region, and the saturation region of the transistor. So let me draw it in a table. So I am writing a table here. First, let me draw the diagram again for the sake of completeness. So this is my emitter, this is my collector, and this is my base. This junction I am calling as emitter base junction, and this particular junction between the base and collector I am calling as base collector junction. So I am writing a table where this is the emitter base junction, this is the base collector or collector base junction, whatever you call, and then this is the region of operation. So let me write the region of operation. So these are the three columns of this particular table that I am trying to draw. Okay. So the first possibility is that the emitter base junction is forward bias. And for this particular forward bias possibility, the base collector junction can be reverse biased. Also for the forward bias emitter base junction, again the base collector junction can also be forward biased. This is the first case. In this case, what we call if the emitter base junction is forward bias and the base collector junction is reverse bias, the transistor is known to operate in an active region. Second possibility, when both of the junction are in forward bias, we call that the transistor is working in a saturation region. Third possibility, that the emitter base junction can be reverse biased and the base collector junction can be forward biased. So this is the case just opposite to the active region. In the active region, we were having the forward bias for the emitter base junction and reverse bias for the base collector junction. So we can call it as a reverse active. And the last possibility is that both the junctions are reverse biased, and this is called as the cutoff region. So these are the four regions of operation for a bipolar junction transistor. Now in this question, it is asked that which of the three region of operations it is, means the particular transistor is operating in which of the following region of operations. So for that, we have to identify the different junctions. Firstly, we have to identify the potential of these two junctions. Means first find the potential of the base junction, let's call it as BB. Find the potential of the emitter junction, VE. Similarly, the potential of the collector, that is VC. Based on these voltages, we will be able to identify whether the emitter base junction is forward biased or reverse biased. Similarly, whether the base collector junction is forward biased or reverse biased. And if we know that thing, it will be easier for us to identify the region of operation. So our task is to find all these voltages. So let's start the question. So this was the basic understanding of all region of operations. Now we are actually trying to solve this question. So we will be actually applying the KVL rule here, Kirchhoff's voltage law. That law will actually help us to find all the currents and voltages. So what I am assuming is that the arrow actually indicates the direction of the emitter current. So this is the direction of IE. That means the current in the emitter is going upward. And as we know, a relation that IE, the emitter current, is equal to the base current plus the collector current. That means this current, using the KCL, Kirchhoff's current law, will be divided between these two currents. That means at this junction the current IE is coming, so the base current will be going like this, and similarly the collector current will also be going forward, upward. Then we have a relation like the current gain for common emitter and common base configuration. So the relation is that the ratio of IE and IC is equal to alpha. That means IE is equal to IC over alpha. Similarly, the collector current and the base current has a relation that IC is equal to beta times IP. So beta is given to us, so we will be using this particular relation, and from this relation we can also find the relation between IE and IP. So I am writing this IC in this first equation, so we will be writing IE as IB plus beta IB, that is nothing but beta plus 1 IP. So these two relations we can actually use to mark the currents. So we can actually deal in a single variable IP. Okay, let's now use the Kirchhoff's law. So if we use the Kirchhoff's law, again let me write the currents. I'm going to the next page each time, so I have to write those currents. That's fine. Okay, so I'm starting from this 0 point, so the potential is 0 here. Then I go to the potential source and the last terminal is negative, so it is -3. Then this is current, we are going in the opposite direction of the current, so this will be 7 IP. 7, I am assuming that the current will be in milliamperes, so this kilo ohm and the milli will cancel out, so it is 7 IP only. Then this is a base emitter junction, and in the question it is given that we are dealing with a silicon transistor. That means the base to emitter voltage drop will be 0.7. So that means we can assume that VBE, voltage gap between emitter to base, is 0.7. So if we are going from here to here, you will actually add up a voltage of 0.7. So let me, okay, just I am writing this equation again here. So this is 0 minus 3 plus 7 IP plus 0.7 for this junction. Then we are at a 500 ohm resistance, so you can write the 500 ohm as 0.5 kilo ohms. So it will be 0.5 IE, and then you go back to the ground, so it is 0, and that should all be equal to 0. Now using the relation that IE, the emitter current, is nothing but beta plus 1 IB. Beta is 100, that is 101 IB. We can substitute this relation IE equals to 101 IB in this first equation, and we will have a complete equation in IB, and from that we can solve for IB, and if we solve it, we will get 46.95 microamperes as the base current. So this is the first value we are getting. Then again we can use this second relation that IE is equal to 101 IB. We will be able to find the emitter current as 4.74 milliamperes. Then the third thing, we can also find the collector current. Collector current is nothing but beta times IP. Beta is 100, that means it is 100 times IP. So we will obtain IC, the collector current, as 4.69 milliamperes. So these are the three values of current we are getting. So this is the first step of calculation, because after knowing all these currents, we will be able to find all these voltages, VE, VB and VC. Okay, now let's find all these voltages. We will use again the Kirchhoff's law or the voltage division laws. So this is VC that we want to find. The current is going upward, IE, and this voltage is 0. That means you can easily say that 0, not so, this is not VC, this is VE. So 0 minus VE should be equal to the current flowing in the circuit, that is IE. Just a moment. Yeah, this is IE. So this is 0.5 times of E. So from here we know IE in milliamperes. So we can find that the emitter voltage will come out to be negative 2.37 volts. On the similar note, we know the potential difference between the base and the emitter, that is 0.7. So that means the emitter the base voltage using that expression will be negative 3.07 volts. Just subtract 0.7 from this, you will get the base voltage. Then the last part of this question is that what is the this voltage VC? We have to find the VC voltage also. That can also be found because we know the collector current is going upward, that is IC. So we can write that the voltage difference VC minus 10 should be equal to the collector resistance times the collector current. IC is known to us, so we can find VC directly from here. If we solve this equation, we will get VC to be 4.07 volts. Okay, now we know all the voltages across all the three terminals. We will be able to identify the reason of operation, or firstly to identify whether the junction is forward wise or the reverse wise. So we know that this is a PNP transistor. That means it is P type, the base will be N type, and also the collector will be P type. And if we consider the base and emitter junction only, so emitter voltage is negative 2.37 and the base voltage is negative 3.07. That means the emitter voltage is more than the base voltage. And from this we can say that this junction, the emitter base junction, is forward wise. Similarly, if we see the voltage across the collector, it is 4.07, and if we see the voltage across the base, it is negative 3.07. That means the voltage across the collector is more than the voltage across the base, and that says that P-type semiconductor has a more potential, so it is also in forward wise. So both the junctions are in forward wise, and that indicates that, let's go to the table again if we have forgotten that. So if both the junctions are in the forward bias condition, we say that the transistor is operating in saturation region. So we can directly say from here that the transistor is operating in saturation region. So this was the first part of the question. We have clearly identified the region of operation. Then the second part is to find the output voltage V0, that we have already defined because BC is nothing but the output voltage. So output voltage in this case will be 4.07 volts. So both the parts are now complete. Now let's go to the last part of this question, where it is asking that what should be the resistance R, the emitter resistance R, that was in this particular question given as 500, but instead of 500, what should be this value so that the transistor operates in the active region. Okay, so let's try that. So what we can say, we can just do the same calculation. We can repeat all the calculations again just by removing this 500 and replacing it with a capital R, a unknown resistance that need to be calculated. So we will do all the calculations again. This is IE going upward, this is IB going left, and this is IC that is going upward again. And we can use the Kirchhoff's voltage law on this particular equation. And if we write the equation again, we will get, now I am assuming that this R in kilo ohms, some value in kilo ohms, because this will be easier for us to write the kilo ohms multiply by milliamperes to be a single unit. Okay, so let's write it. So we are starting from this point. So this is 0. So we'll write 0 minus 3 for this potential source, then plus 7 IP, then the base to emitter voltage, that is 0.7, then this is voltage across this R resistance, that is R times IE, and we are going back to the ground. Again we can use the relation that IE is nothing but 101 IB, beta plus 1 IB, and we can substitute it here. So we will get a current IB in terms of capital R, and if we solve this carefully, we will get IB to be 2.7 over 7 plus 101 R. So this is the first equation. From this we can directly find the correct emitter current, that will be 101 times of this IB, so it will be 2.7 times 101 over 7 plus 101 R. So this is the second equation. Similarly, IC, it will be beta times IB, that is 100 times of the IB, because beta is 100, that is given. So it is 2.7 times 100 over 7 plus 101 R. This is the third equation. Now, using these currents, we will again find the voltages. Those voltages will now be in the form of R. So let's write the voltages. So first write the voltage across the emitter, VB, then across the base, VB, and then across the collector, VC. So VE will be just R times of IE, right? So it is negative R times of IE. IE was 2.7 times 101, so it is negative 2.7 times 101 times R over 7 plus 101 R. So this is the fourth equation. Similarly, VB, if you are calculating, you just have to subtract 0.7 from this equation because of the presence of silicon transistor. So it is negative 2.7 times 101 R over 7 plus 101 R, negative 0.7. So this is the fifth equation. Then VC, the collector voltage, you can find again using this relation that VC minus 10 should be equal to IC into 3, and IC we have already calculated. If we substitute that, we will get 100 times 2.7 times 3 over 7 plus 101 R. What I am writing is that this term is your IC, and I am multiplying this IC by 3, so I am getting the potential drop here, and that 10 potential that is given at the top, so that will also be written, so it will be negative 10. So this is my VC voltage and this is my BB voltage. What I want to know is that this we want this particular junction to be in forward reverse bias region, because we want the transistor to operate in an active region, so that this collector base junction should be reverse biased. And for the collector base junction to be reverse biased, the voltage across the collector, because this is P type, okay, and this is N type, so voltage across the collector should be less than the voltage across the base, and we are finding the minimum value, that means it should be less than, slightly less than or equal to. Okay, so this condition we can apply on these voltages VB and PC. So using this equation number 5 and equation number 6, we can actually write this inequality. So let's write this. So what I am saying, the VC should be less than VB, because the voltage across the P type semiconductor should be less than the voltage across the N type semiconductor for reverse bias junction. Okay, so VC we obtained as 100 times 2.7 times 3 over 7 plus 101 R, negative 10, and it should be less than or equal to negative 2.7 times 101 times R over 7 plus 101 R. That was negative 0.7. That was the voltage across the base. Now we can actually rearrange these terms. So we can see that the denominator is common in both the equations, and then 10 can be taken to the other side, and we can rewrite this equation carefully. So if we rewrite this equation, we will get 100 into 2.7 into 3 as the numerator, plus 2.7 times 101 R over, the denominator is common, so I am just taking the LCM and adding them up. and that should be less than or equal to, this 10 will go to the other side and it will be subtracted to 0.7, you will get 9.3. Now again you can take this 7 plus 101R to the other side of the equation, and then you can rewrite this equation as, I am taking 2.7 common in the left hand side, so it is 100 into 3 plus 101R, and that should be equal to 9.3 times 7 plus 101R. Okay, I am writing this equation to the other page so that we can write it carefully and there is no error of understanding. So this is 2.7 times 300 plus 101 times R, and it should be less than or equal to 9.3 times 7 plus 101 R. Now what we can do, we can take the terms containing R to the one side and then the terms not containing R to the other side, and by doing that we will get this as 2.7 times 300, and this negative of 9.3 times 7 should be less than or equal to, this is 101R, I am taking it outside, times 9.3 negative 2.7. So these are the terms containing R and these are the terms not containing R, and we can actually again solve this equation. So we will get R should be greater than or equal to 2.7 times 300 minus 9.3 times 7 over 101 times this 9.3 minus 2.7. You can, okay, let me write it as it is, that's fine. So if we solve this equation, we will get R should be greater than or equal to 1.127 kilo ohms, or R should be greater than or equal to 1127. Not, there is no point here. So 1127 ohms. So if R is more than this value, the transistor will operate in the active region. So that was the last part of the question. So we have successfully solved the complete question by clearly identifying the region of operation, finding the output voltage, and then finding the minimum resistance required for the transistor to operate in the active region. Okay, so we will be continuing this series to solve the UPSC mains physics question. Please like this video, please share it with your friends and subscribe to our channel. Thank you.